differentiability of a function. Let f of x be a function defined in the domain D. Then limit as x approaches x naught of f of x minus f of x naught by x minus x naught. If this limit exists, is called the derivative of the function f of x at x equal to x naught, and is denoted by f prime of x naught or y naught prime or y naught dot. Yes, therefore we can say f prime of x naught is equal to y naught prime equal to y naught dot is equal to limit as x approaches x naught of f of x minus f of x naught by x minus x naught. Now, by the way, remember we also say y is equal to f of x, right? That means this limit, if I write it using this notation, then it would be limit as x approaches x naught of y minus y naught by x minus x naught. This is nothing but the slope of the curve at x equal to x naught. Yes, and remember it may exist or not. Okay, now see, all these things we have already learned in our previous sessions, but here we are looking at it in a little bit more formal manner. Now, if limit as x approaches x naught from the left hand side of f of x minus f of x naught by x minus x naught exists, it is called left hand derivative of f of x at x equal to x naught. Similarly, if limit as x approaches x plus from the positive side or from the right hand side, f of x minus f of x naught by x minus x naught exists, it is called the right hand derivative of f of x at x equal to x naught. Okay, now we come to the critical part. Just like continuity, f of x is differentiable. That means we can find the derivative. Find the derivative means differentiable at x naught if and only if left hand derivative of f of x naught and right hand derivative of f of x naught exist. That means both left hand and right hand derivatives exist and they are equal. So f of x is defined in the closed interval AB. Second is differentiable at endpoints. If endpoint A, if right hand derivative and differentiable at endpoint B, if left hand derivative at B exists, and in such a case f of x is differentiable in a b closed interval if and only if it is derivable at every point of the closed interval a comma b. So f of x is defined in the interval a b. It is differentiable at endpoint a if the right hand derivative exists. It is differentiable at endpoint b if left hand derivative exists. And f of x is differentiable in ab if and only if it is derivable at every point. Yeah, this actually include this and the previous one if you think about it, because it is talking of every point, so endpoints are also included. Now let's look at a theorem. If a function f of x is differentiable at x equal to x naught, then it is continuous at x equal to x naught. Okay, let me complete that, but not vice versa. Its converse is not. Okay, so let's say we have f prime of x is equal to limit as x approaches x naught of f of x minus f of x naught by x minus x naught. Now let's begin with limit as x approaches x naught of f of x minus f of x naught. Now what we'll do is we'll multiply this by x minus x naught by x minus x naught. Yes, which means again using the algebra of limits, what we'll do is we'll split these two up, but this we will take it below this. So f of x minus f of x naught by x minus x naught times a limit as x approaches x naught of x minus x naught. Now this is nothing but f prime of x naught times, and as x naught approaches closer and closer to x, what will happen? It will disappear. So this will become 0. So which means this will become 0. So therefore limit as x approaches x naught of f of x minus f of x naught is equal to 0, which implies limit as x approaches x naught of f of x minus limit as x approaches x naught of f of x naught is equal to 0, which is equal to limit as x approaches x naught of f of x is equal to limit as x approaches x naught of f of x naught. So which means left hand both f of x and the other point, they become equal as x gets closer and closer to x naught. So therefore f of x is continuous at x naught. Now the converse is not true, because even though it may be differentiable, but it may not be continuous. We use some techniques, remember, removable discontinuity. And okay, so let's do a few problem solvings. One, let's say f of x is equal to x square minus 1 when x is greater than or equal to 1, and 1 minus x when x is less than 1, and we are interested in knowing its differentiability at x equal to 1. Okay, so let's look at left hand derivative at 1. So limit as x approaches 1 from the left hand side of f of x minus f of 1 by x minus 1. Now let's simplify it a little bit. So limit as x approaches 1 from the left side, f of x minus left hand side means it will be less than 1. So it means it is 1 minus x, and 1 minus x is 0, right? X minus 1. So now let's rewrite this in terms of h, as h approaches 0 of f of 1 minus h by 1 minus h. Again, remember we are coming from the left hand side, minus 1. So now this, what happens? We get, now since we are coming from the left hand side, is less than 1. So f of x is equal to 1 minus x. So we can say limit as h approaches 0. Now instead of x we put 1 minus h. So we get 1 minus 1 minus h, right? So 1 minus 1 minus h by, these two get cancelled out, we have minus h. So we'll leave it as it is because it is not a function. Okay, so now limit as h approaches 0 of 1 minus 1 plus h by minus h. These two get cancelled, these two get cancelled, and we are left with a constant, that is minus 1. So which means minus 1. So this is the left hand derivative. Now let's look at the right hand derivative at 1. So limit as x approaches 1 from the right hand side of f of x minus f of 1 by x minus 1. Again, let's simplify it. Now it is coming from the positive side. So the function that we have to look at is x square minus 1, right? So f of x minus 1 square minus 1 is 0 divided by x minus 1. Now let's write it in terms of h. So since we are talking of from the right hand side, 1 plus h by 1 plus h minus 1. So these two get cancelled out, and here remember f of x is x square minus 1. So 1 minus h, 1 plus h square minus 1. This is f of x. So which is equal to 1 plus 2h plus h square minus 1. So these two get cancelled out, and we are left with limit as h approaches 0 of 2h plus h square by h. And we take the limit and simplify it a little bit. So h we take out common. So 2 plus h by h. This h gets cancelled. And now we take the limit. So we get 2 as h goes to 0. Now you might have noticed that the left hand derivative at 1 is not equal to right hand derivative at 1. So therefore f prime of 1 does not exist. That means it is not differentiable at x equal to 1, even though it is continuous at x equal to 1. Okay, so let's look at the next problem. Let's say f of x is equal to x square sine 1 by x when x is not equal to 0 and 0 when x equal to 0. And we are interested in its differentiability at x equal to 0. So like left hand derivative at 0 is equal to limit as x approaches 0 from the left hand side of f of x minus f of 0 by x minus 0. So limit as x approaches 0 from the left hand side of f of x minus, now if it is coming from the left hand side, that means it is less than 0. So less than 0 means not equal to 0. So not equal to 0 means x square sine 1 by x. So let's substitute 0 to this. That means this will become 0. So 0 minus x minus 0. Now let's write this in terms of h. As h approaches 0 of f of 0 minus h by 0 minus h. So limit as h approaches 0 of f of minus h means what? Minus h square sine 1 by minus h. Now this would be h square sine minus 1 by h. This minus we can take it out. So we get limit as h approaches 0 of minus h square sine 1 by h by minus h. So minus minus gets cancelled, one of the h gets cancelled, and when we take the limit, this becomes 0 and this sign, remember this is oscillatory, so it will go between minus 1 and 1. But since this becomes 0, ultimately this will become 0. So the left hand derivative is 0. Now let's look at right hand derivative at 0. So limit as x approaches 0 from the right hand side of f of x minus f of 0 by x minus 0. Now limit as x approaches 0, or let's say h approaches 0 of f of 0 minus h plus h, because we are talking of right hand, f of 0 by 0 plus h minus 0. Okay, so let's simplify this. H approaches 0 of f of h minus f of 0. Now we are coming from the positive side. It is still not equal to 0. So again we will be using x square sine 1 by x. So now what happens? F of 0. So this becomes a 0 by h minus 0. So this we don't need to write. Now f of h would be what? H square sine 1 by h. So h square sine 1 by h by h. So these two get cancelled and we are left with limit as h approaches 0 of h sine 1 by h, and this goes to 0 again. Okay, so the left hand derivative at 0 is equal to right hand derivative at 0 is equal to 0. And now we also have to see whether it exists, whether it is defined at 0. So f prime of 0 is, as per our problem statement itself, it is equal to 0. So therefore the function is differentiable at x equal to 0. So that is differentiability. Enough for today. Bye.